Okay, this evening we are going to talk about multiplication rules for probability. These are used when you are trying to calculate the probability of something and then something else happening. So, like the probability of rolling a 4 after rolling a 6 on a die. Um, you may remember we talked a little bit about what happens if we had an either or situation, the probability of rolling a 6 or a 4, for example. Um, Now we're going to do the next logical step of and. So something and something else. Get in the right window. There we go. Uh, these use what's called the multiplication rules for probability. Um, and so we need to start with some definitions. Uh, First off, we've got multi-stage experiment, which is an experiment with two or more steps or stages. Um, draw one card, draw a second card, roll one die, roll a second die. Um, an experiment with replacement means you put the whatever you're dealing with back into consideration before performing the next stage. So, for example, if I'm drawing a card, if I'm doing this experiment with replacement, I put that card back in the deck before I draw the next card. Um, Two events are independent if one event happening does not influence the probability of the other event. So, with the example of drawing uh, cards, if I draw a card, record what I've done, put it back in, shuffle, the next draw is independent of that first draw. Okay, if we have two independent events, E and F, the probability of E and F occurring is the uh, product of the probability of E times the probability of F. Can't believe I just blanked on the word product. Uh, Apparently it has been a long day. Okay, so here's our example. We've got the deck of cards example. Let me pause and see if I can. Okay, deck of cards. So, what is the probability of choosing a king, then a queen? Standard 52 card deck. First question you'll need to ask yourself is are we doing this with replacement? In this case, we are. Oh, yes, it does. So, are these independent? Yes. So, standard 52 card deck. Are independent. So, we're going to go ahead and try to calculate this. Move on when you're ready. Think about how many kings and queens there are in a standard deck with 52 cards. Okay. Alright, so using the multiplication rule, we have that we want the probability of king and queen with replacement. So it's probability of king times probability of a queen. So 4 kings and 52 cards. Whoop. Apparently the probability of me playing 52 card pickup while recording this is very high. So a 4 in 52 chance of getting a king and a 4 in 52 chance of getting a queen. So there's a queen. Replace it. Shuffle. You can see they've done the math there. 4 in 52 is 1 in 13. Second draw is a 6, so I did not get it. And there is only a 0.59% chance of that draw anyway. So, not surprising that I did not get a king the second time. Alright, another example is let's say that HR has found the probabilities of employees being written up for a few infractions given in this table. So, fairly high probability of being written up for being late for work or for taking unauthorized breaks. Lower probability of being written up for failing to show up, probably because it doesn't happen as often. All right, if we assume each infraction is independent of the others, what is the probability that a given employee will be written up for being late for work? Let me get my highlighter. Here, let's get a highlighter. Yeah. Late for work. Taking unauthorized breaks. And leaving early. There we go. Laser pointer. There we go. Okay. So once you go ahead and do that calculation, and a few more cards, do that calculation and unpause when you're ready to move on. Okay, since we've already noted that these three events are independent, we can just use the multiplication rule that we've just gone over to solve for this. Right? So probability of late for work times probability of leaving early times the probability of unauthorized breaks. Let's see, we've got late for work, leaving early, and unauthorized breaks. So there's a 1.5% chance of an employee being written up for all three of those. Okay. So that was an event performed with replacement. An experiment performed without replacement means the objects are not placed back into consideration. So if I draw my card here and I set it aside, then that changes the probability of what is going to happen next. I'm doing this without replacement, so I have not replaced that card in my deck. Easy way to remember it, even if you're not dealing with cards and such. The other thing that means is these two events become dependent. Because I've removed a deck, I've now got 51. Removed a card, I've now got 51 cards in my deck. So I've affected the probability of whatever the next is. So how would we do this? In this case, it's going to be similar. It's without replacement and dependent. It's basically unchanged in other ways, though. We can think about this in two stages. We've got, the probability of drawing a king is still 1 in 13, right? So there's my first card, set it aside. Now I've only got 51 cards, thus the probability of getting a queen, if the king was drawn first, without replacement, is 4 in 51. That's not going... fairly certain 51 is a prime number. That's not going to divide nicely and, reduce. So I can just multiply those and get 0.6%, which is actually ever so slightly higher than the 0.59, I think it was, we had. Okay, now we have what's called conditional probability. And we've got this little mathematical notation to denote it. F, I want to call this pipe because I've done too much scripting and stuff, and that's what that symbol is used for. Straight line, E. So the probability of F happening given E happening first is what we've got looking at here. So if we, draw a card out of our deck without replacement, so we don't put it back, what is the probability of drawing a second card and having it be red if the first card was a diamond? My first card happened to be a diamond. Nice. Alright, so first thing we need to do is figure out how many red cards are left after the first pick. Half of the deck is red, half of the deck is black, so there's 26 of each. Drawn a diamond, so that's a red card, so now I've only got 25 diamonds, or 25 red cards, diamonds and hearts, in the deck. There are also only 51 cards total, so I've got 25 over 51 for the second one. Okay. Alright, so now we have a multiplication rule associated with this. This one will kind of make more sense in a minute. This is, the probability of E and F occurring is the probability of E occurring times the probability of F occurring after E occurs. It is also the probability of F occurring times the probability of E occurring after F occurs. Same thing. Alright, so let's see an example of this. Put my queen back in. The probability of choosing two face cards in a row without replacement. So, we're dealing with dependent events. We're not replacing them. So we need to use the multiplication rule for probability of dependent events. First card is picked. All 12 face cards are available. I'm drawing a 6, so that's not a face card. When the second card is drawn, if the first card was a face card, there are only 11 face cards left and 51 cards remaining. So we have probability of a face card, which is, there's 12 face cards, 12 of 51, 12 and 52. 51 is not a prime number. Okay. So you can see they first reduced this fraction to 3 over 13. Then they noted that 51 divided by 3 is 17, so they reduced that. This is a multiplication, so you can swap the order around pretty easily without messing anything up. That simplifies things a bit, and we get 4.98%. So you can think of this as, the probability of drawing a face card and then a face card in a dependent scenario is this. Oh, okay. Slightly less gambling-related example. If we've got 17 men and 24 women in the Rotary Club, and 2 members are chosen at random each year to serve on the scholarship committee. What's the probability of choosing 2 members at random, and the first being a man and the second being a woman? So this is going to be without replacement. You can't put the person in to be potentially chosen a second time, right? So the first choice is going to influence the possibility for the second choice, because I would assume we don't want to choose the same person twice. So we're dealing with dependent events. So we've got the probability of choosing a man and then a woman, which is going to be using this formula: probability of choosing a man Then probability of choosing a woman given a man was chosen first. Okay, so we had 17 men and 41 total. Right. So the probability of choosing a man is 17 out of 41. Once we've picked somebody, we've only got 40 remaining, so there's 24 women out of 40. So the calculation becomes 17 out of 41 times 24 out of 40. We can simplify the 24 out of 40 by dividing both by 8. And we get, 24.88%. We can also, if you think back to this in terms of E and F, E times F after E, we can rearrange that formula in this way, so that if we don't know this probability, but we can find these two easily, we can solve that. Do note that if E and F are independent, then the probability of E given F is the same as the probability of F. Right, so if E and F are independent, this probability is equal to the probability of just F. Alright, so let's look at an example using this. If we've got 300 applicants, 212 are female and 110 are female, one of those... 212 are female and 110 are female with a graduate degree. Okay, 212 are female, so the remainder are male. Got it. I was expecting a male-female dichotomy, and it threw me for a minute. So what is the probability that a randomly chosen applicant has a graduate degree, given that the applicant is female? All right. So we don't know the number of males with graduate degrees in this instance, so we can't just calculate that directly. We know how many females have a graduate degree and how many females there are. Right. Next question is, if 152 have graduate degrees, what is the probability that a randomly chosen applicant is female, given the applicant has a graduate degree? Alright, let's move on to the solution. So we're after applicants with a graduate degree, given that the applicant is female. So to use the formula we saw a moment ago, we'd need to know the probability of having a female and a graduate degree, as well as the probability of female. And that is the information that was given to us in the beginning. There's, 210 female and 100 females with a graduate degree. I don't have the numbers in front of me anymore, so I'm trying to remember. It's not technically multi-stage, but it's kind of easier to think about it in stages, because, narrowed it down with one criteria, then narrowed it down with another. So, we can use our formula for conditional probability. Out of our 300 total applicants, 110 are females with a graduate degree, so that probability of female and a graduate degree is 110 over 300. One of the things you can see from this is which formula you want to use really follows what data you have. And I am just dropping my cards all over the place, so I need to put them down. with this particular data set, this formula is what's going to work best for us. With if the data had been presented differently, a different formula might have worked. What we use really depends on what we have and what we're given. Um, Same thing, we've got the probability of choosing female applicants in general is 212 over 300. So our conditional probability is if choosing a graduate degree after having chosen female is there we are, female with and a graduate degree divided by probability female. So that's this. You can cancel up the 300s. Yeah, okay. I'm not used to quite writing those types of problems out so much, but you can see they've rewritten this with different notation, then inverted and multiplied, canceled the 300s, simplified a little bit, divided both of those by 2, and came up with 0.51, okay, roughly 52%. So this asks for the reverse of what we got in part A, what the probability would be of getting a female given we decided on somebody with a graduate degree. We know from part A that we've got 110 females with graduate degrees. That's 110 over 300. From what was given in part B, we know that there's 152 total graduate degrees out of that 300. So we've got that same formula. Female after choosing graduate degree is female and graduate degree over graduate degree. So again, 110 over 300 divided by 152 over 300. Invert and multiply, cancel the 300s. Those again are both even numbers, so we can simplify a little bit by dividing by 2, and we get 55 over 76, or roughly 72%. So one of the things this does show is that the order you choose things matters. We're more likely to get a female. In this situation, we're more likely to hire a female given we're looking for a graduate degree than we were likely to get a graduate degree given that we were hiring a female. We also have the fundamental counting principle. If we've got a multi-stage experiment with some number in stages, so in could be 2, so if I'm drawing 2 cards, it could be, pick up some of my cards because they're bothering me down there. It could be 6 if I'm drawing 6 cards, however many it is. The total number of possible outcomes is the possible outcomes from the first stage times the possible outcomes from the second stage times the possible outcomes from the third stage on to however many stages we have. We did kind of see this with dice with group on Wednesday. If you roll 1 die, there's 6 possible outcomes. If you roll 2 dice, there's 6 outcomes for each dice, or 36 possible outcomes. If I was rolling 3 die, there'd be 36 times 6, which I don't know off the top of my head, etc. As the more die I add, the more I multiply by. If one of those, if I was rolling 2d6 and 1 4-sided die, it'd be 6 times 6 times 4. If one of them was 20-sided, 6 times 6 times 4 times 20, um, however many possible outcomes there are. So if with the card drawing thing, I've got 52 cards for the first one. If I'm doing it without replacement, I've now got 51 possible outcomes. So my total number of outcomes would be 52 times 51. If I draw another one and now I've got 50 cards, it'd be 52 times 51 times 50, etc. With changing by how many cards I draw and whether or not I'm doing this with replacement. Okay, so if Kilby starts an online degree program in July and she gets randomly assigned to some 4 different core courses, we've got 8 sections of English, 12 sections of algebra, 11 sections of American history, and 5 sections of physical science. How many options are there for her schedule? Given the formula we just saw, go ahead and work that out and unpause when you're ready to move on. Okay. So we've got 4 slots to fill. 1 for each course. First slot is English. We've got any of the 8 English 1 sections. Next one was called Algebra. Any of those would work. Same thing with American history and physical science. So each slot has the probability of, the number of outcomes equal to the number of sections there are. So it's 8 times 12 times 11 times 5, or 5,280 possible options for her schedule. Okay, next example. Again, this is without replacement. If a local charity is electing a new vice president and secretary, excuse me, to replace some outgoing board members, we have 11 members who don't already hold an office. In how many ways can the 2 positions be filled if no one can hold more than 1 office? So I couldn't choose one of those 11 members for both vice presidents and secretary. Think about that, try it out, and move on when you're ready. Okay, we've got 2 slots. We're doing this without replacement, so once somebody's chosen for one office, they cannot be chosen for the other. If we, pick somebody for the first, we've got 11 choices for the first, then that only gives us 10 choices for the second. So it's 11 times 10, so 110 possible ways to elect new officers. Okay. If Robin is preparing snacks for her twins, Matthew and Lainey, and she wants to give each child 1 item, and she has carrots, raisins, crackers, grapes, apples, yogurt, and granola bars on hand, if she randomly chooses 1 snack for each child, what is the probability that each child gets the same snack as yesterday? Okay, so what are the number of ways that she could randomly choose a snack? Let's think of this as having, two slots to fill, 2 baskets, 2 plates to put snacks on, however you want to think of it, 1 for each twin. There is no requirement that the twins have different snacks or the same snack. There are 7 possibilities for each child. The choices are made with replacement. The implication of that is that there is enough of all 7 of these that she's not going to run out before she can give something to the second child. So there are 7 times 7, or 49 possible ways she can prepare the snacks. Alright, so if we, how many ways could she possibly choose the same snack as yesterday for each child? And that's going to be one, assuming that each child only gets one snack in the afternoon, and yeah, that is probably a safe assumption. Um, or rather, it should be safe to assume that each child is given one snack in the afternoon. I know for my own children that it's not necessarily a safe assumption that they haven't gotten their own. Um, okay, so we've got one way that it could possibly be the same. So we've got one way to choose the same snack and 49 total snacks, or 2.04% chance that each child will eat the same thing 2 days in a row. Okay, so that gives you an example of how that's useful. Another example besides with die. And that is it for this section.